In section 2.2 of the class, we're going to begin studying and analyzing functions. Before we get to the definition of a function, we want to talk about a more general object, which is called a relation. A relation is any set of ordered pairs. The set of all first components of the ordered pairs is called the domain, and the set of all second components is called the range of the relation. An easy way to kind of keep this in mind is if you think of like ordered pairs, especially back like when you used to graph things, x comma y, the x always comes first and the y comes second, and each element, the first elements, will belong to what we call the domain set. The second elements will belong to the range set. So very similar to how it's like x before y, alphabetical order, the domain number comes first, the range number comes second. In example 1, we have a relation, and we're asked to write out its domain and its range. Let's go ahead and find the domain first. Remember, the domain, those should be the x values, those are the first numbers within each ordered pair. The domain of this relation is going to be 0, 10, 20, and 30. The range is going to be the corresponding y values. That's the second entry in each ordered pair. That's going to be 9.1, 6.7, 10.7, and 13.2. These are just sets, but one of the things commonly you will see done is oftentimes people will order the sets. So even though we do have the correct range set, some people will kind of go back through and put the numbers in order. So like 6.7, 9.1, 10.7, and then the maximum, the largest, was 13.2. Okay. Either way would be acceptable because they're just sets for right now. A function, as it turns out, is a very special type of relation. A function is a correspondence from a first set, which we call the domain, to a second set called the range, such that each element in the domain corresponds to exactly one element in the range. Okay? And in general, these sets can be very abstract. They don't necessarily have to be numbers, although for the sake of our course, oftentimes they will be. They could represent things like people's names, geographic locations, temperatures, social security numbers, etc. But the basics behind a function is that each element in the domain corresponds to exactly one element in the range. If we look at the following depictions, the relations given by the first set and by the second set, these would be examples of functions. If we look at kind of the first set of ordered pairs that are graphed and mapped out, remember the first element in each ordered pair is the domain. So A, B, C, and D, that would be the domain of this relation. The range would be the values Q, P, S, and R. So that's our range. And what we notice is that every single value in the domain is relating to just a single value in the range. So A relates to Q, B relates to P, C relates to S, and D relates to R. So that would make this a function. So this is a function. If we look at the second relation, A to 1, B to 1, and C to 2, this is also another example of a function. The domain set would be A, B, and C. The range set would be the values 1 and 2. What's important here to notice is that each element in the domain is corresponding to only one value in the range. A is associated to 1. B also happens to be associated to 1, which is perfectly fine. And C gets associated to 2. Notice we wouldn't even really need to write the 3 there, since 3 wasn't part of the range set. Nothing gets demonstrated to 3, but this is another example of a function. if we wanted to see an example of a relation that is not a function, let me make one up. Let's suppose we had the following. I'm going to work off of kind of this last example. Let's suppose we had a to 1, b to 1. Suppose I add c to 1, and I'm also going to add c to 2. So we have two sets, the domain and the range. The domain would be the values a, b, and c. And then I have the numbers 1 and 2 in the range. A gets associated with 1. B gets associated with 1. But the last two ordered pairs say that c goes to 1 and c also goes to 2. And because of that, that is not a function. The reason why this is not a function is we have one value in the domain that's getting associated to more than one value in the range. So with c going to 1 and c going to 2, that means that this relation would not be a function. An easy way to see this, if you have simply a set of ordered pairs, if you're looking for kind of like a hard and fast rule, as long as the first value does not get repeated, so as long as none of the domain values get repeated, then that would be a function. So in this last example, notice that we had the value c, we had c comma 1 and c comma 2. Because the first number was repeated, that stopped this from being a function. Whereas it's possible, and we saw this earlier, this relation we said was a function. Notice that the y value, the range value 1, was repeated. That's okay, that can still be a function, provided that the first values, the domain values, are not repeated. Okay. Let's take a look at example 2. They want us to determine whether each relation is a function or not. If it is not a function, explain why. In the first relation, we have 1, 5, 2, 5, 3, 7, and 4, 8. Our domain is 1, 2, 3, and 4. Notice that none of those domain values get repeated. The domain value 1 appears once. Same thing with 2, with 3, and with 4. So this would be a function. So the relation in A is a function. Okay. If we look at the relation in part B, we have 5, 1, 5, 2, 7, 3, and 8, 4. Because of these first two ordered pairs, this is not going to be a function. The reason why this is not a function is we have a value in the domain. I'm just going to draw a partial of it, namely the value 5, that is associating to more than one value in the range. We have 5 related to 1, and we have 5 related to 2, and because of that, that will not be a function. The value 5 in the domain corresponds to more than one value in the range. And that's exactly why it's not a function. The next thing we want to get used to is functions as equations and function notation. Functions are usually given in terms of equations rather than sets of ordered pairs. We can think of the domain set as the function's inputs, so those are the things that we plug into the function, and the corresponding range values would be the outputs we get from the function. The variable x will be called the independent variable because it can be assigned any value from the domain, and the y value will be renamed with f of x, which is going to be called the dependent variable. We think of y as depending upon our choice of x, so y will be the dependent variable. In example 3, we want to determine if each equation represents y as a function of x. Okay. So we're asking the question, does each equation represent y as a function of x. Y would be a function of x if every unique value for x we plug in would produce a unique value for y. So remember, that's the heart of a function, is that every value in the domain has to produce exactly one value in the range. Oftentimes, you can answer this question by trying to solve the expression for y. In example 3, part A, we have x squared plus y equals to 1. If I want to get the y by itself, I can subtract x squared from both sides. The x squareds cancel. We get y equals 1 minus x squared. Notice that for every value of x we plug into here, we did get the y by itself. For every value of x we plug in, we're going to get a unique output. Whenever you take a real number and you square it, there's just one value. And then we're taking that one value and subtracting it from 1. So this is a function. So in particular, what we mean to say is that y is a function of x. Okay. Typically, what we would do here, instead of saying y equals, we would use the function notation now, which we'll talk about in a minute. We would say f of x equals 1 minus x squared. Every value x in the domain would produce a unique value y in the range. Let's take a look at part B, same question. We want to ask, does this equation define y as a function of x? To do that, let's try and get the y by itself. We would begin by first adding x to both sides. Here this cancels. We get y squared equals 1 plus x. Now to get the y by itself, we're going to have to take the square root of both sides. But be careful. Remember, if you take the square root of a real number, that has two square roots, both the principal root and a negative root. The square root and the square cancel, and so we get y equals plus or minus the square root of 1 plus x. And because of this plus and minus quantity, this is not going to be a function. So y is not going to be a function of x in this case. To see that more in depth, let's just pick a value for x. It's going to make it really easy. Watch what happens if we choose the x value 0. If we take 0 and plug it into here, we would get y equals plus or minus the square root of 1 plus 0, which is y equals plus or minus the square root of 1, which is y equals plus and minus 1. So what's happening with this particular equation is we have one value of x in the domain, namely the value 0, which is getting associated to two numbers in the range. And x value of 0 corresponds to both y positive 1 and y negative 1. And so because of that, this is not a function of x. The notation that we use, this here, be very careful, it does not mean multiplication. Even though we use like a parenthesis, this is read f of x, or some people will even say f at x. The next important thing that we want to get a handle on, it's a very important skill set, is the ability to evaluate functions for certain values. For example, we want to find the value f of 4 for f of x equals 2x plus 3. F of 4 represents the output we get from the function f when we plug in the value x equals to 4. One of the best tips that I'll probably give you all semester when it comes to function evaluation, and it might not necessarily matter early on, but when the evaluations get more abstract and more involved, this would be very helpful. You can think of the x as like a placeholder for a real number. Okay? So given the equation f of x equals 2x plus 3, what I like to write out is what I call the statement form of the function. And all that involves is simply replacing the variable x with a parenthesis. At its heart, what this function f of x is telling us to do is it says to take your input, whatever that input may be. Usually we call it x. We're going to take that input, we're going to multiply it by 2, and then we're going to add 3 to it. So if we want to evaluate the function f at 4, if I have my statement form written out, then that will give us a place to plug the number 4 into. So everywhere I see an x, I'm going to put the number 4. And now we just have to use order of operations to compute this value. 2 times 4 is 8. And then 8 plus 3 is 11. So we would say that f of 4, meaning the value of the function f with an input of 4, is equal to 11. Okay. So the 4 is your input. That's our x value. That's the value coming from the domain. The function f associates to that value 4 the unique number in the range, which would be the output of 11. And we summarize that relationship by saying f of 4 equals 11. Let's take a look at the next one. We want to find g of negative 2 for g of x equals 2x squared minus 1. So let me just copy this down. G of x is a function such that we take our input, we square it, we're going to multiply it by 2, and then we're going to subtract 1 from it. So I've copied down my statement form. Looks like this. And now we are asked to evaluate g of negative 2. So everywhere we see an x in the expression for g, I'm going to replace it with the value negative 2. G of negative 2 equals, order of operations, we have to do the exponent first. Negative 2 squared means negative 2 times negative 2, which is positive 4. 2 times 4 is 8. And then 8 minus 1 should be 7. So g of negative 2 is equal to 7. Let's take a look at the next one. We want to find h of negative t. So we're evaluating this function. Here it's h is a function of r. So the independent variable was r. Everywhere we see an r, we're replacing it with negative t. So it should look like this. Once we have it substituted in, we just want to simply simplify this. Negative t cubed means negative t times negative t times negative t, which is going to end up being a negative t cubed, minus 2 times negative t squared will end up being a positive t squared, still multiplying it by the negative 2, and then we have a plus 5. So the function h evaluated at negative t gives us this, negative t cubed minus 2t squared plus 5. If we go back and contrast what we got from parts A and parts B, notice that in part A and part B we plugged real numbers into the function. We plugged in 4 and negative 2, and our outputs were real numbers. We got out the values 11 and 7. In example C, we took the function h and we evaluated it at the algebraic quantity involving the variable t. Not surprisingly, the answer we get ends up being an algebraic quantity involving the variable t. So h of negative t is negative t cubed minus 2t squared plus 5. Let's do another one of these. Let's find f of a plus 2 for the function f of x equals 5x plus 7. So I'm just going to simply begin by copying down the statement form. This function capital F says to take your input, multiply it by 5, and then add 7 to it. We're trying to find f of a plus 2, so everywhere we had the x, we're replacing it with the quantity a plus 2. Now that we have it substituted in, let's try to simplify this. We can distribute the 5 through. This will give us 5a plus 10 plus 7. And then lastly, we can combine some like terms. 10 plus 7 gives us 17. So f of a plus 2 is equal to 5a plus 17. Oftentimes we can have a function that's defined by more than one piece over its domain, and that's what we refer to as a piecewise defined function. Here, in example 5, we're given the function f of x, which is equal to, and a lot of times you'll see like commas here, f of x is equal to x squared plus 1, so it's this piece when the value of x, when the input is less than 0. And it's going to be x minus 1 if the input x is greater than or equal to 0. For example, if we wanted to evaluate this piecewise defined function, if we wanted to evaluate f at -1, we have to determine which part do we plug the -1 into. Do we plug it into the top part, which is x squared plus 1, or do we plug it into the bottom part, which is x minus 1? And to determine which piece it goes into, we need to see which test condition the -1 satisfies. Is -1 less than 0? Well, the answer is yes. So because that satisfies the first condition, that means it goes into this top part. This is going to be -1 squared plus 1, which is 1 plus 1, which is 2. So f of -1 equals to 2. Whenever we work with piecewise defined functions, it'll always be the case that whatever x value or value you use will only ever satisfy one of the test conditions. Let's take a look at the next one. If we want to find the value f of 0, notice that 0 is not less than itself, so that would be false. But 0 is greater than or equal to itself because of the equal component. So because x equals to 0 satisfies this condition, it gets plugged into that piece of the piecewise defined function. This is going to be 0 minus 1, which is -1. So f of 0 has the value -1. And then lastly, for f of 1, that's not less than 0. It is greater than or equal to 0. So it too gets plugged into the bottom part. That's going to be 1 minus 1, which gives us 0. One of the types of expressions we're going to work a lot with in this class, and will be used in quite a few other classes, is an expression called the difference quotient. Okay. And I'll actually derive this and show you where this formula comes from when we start to talk about average rate of change. But right now, the difference quotient for us, please make sure you have this formula memorized. We do want you all to kind of memorize this. The difference quotient is f of x plus h minus f of x divided by h. So you'll be given a function. We'll give you the expression for it. And what we will want to do is plug it into this difference quotient and simplify it. When working with the difference quotient, there's always the same 3 key pieces. The denominator is the easiest. It's just always going to be the expression h. And in the numerator, we have the difference of 2 function values. We have the second one is f of x, which will be just the expression or equation they give to us. And then the first one will require us to do an evaluation. That's finding the function f evaluated at the quantity x plus h. And usually this is the part of the difference quotient that requires kind of the most work up front. Let's take a look at with example 6. It's kind of a leading question where they're going to walk us through this one. If we have the function f of x equals 3x plus 7, Let's find and simplify each of the following things. The first part we want is f of x plus h. In order to find that, let me copy down my statement form. F of x says to take your input x, we're going to multiply it by 3, and then we're going to add 7 to it. Here I'm plugging in, I want to evaluate it at x plus h. So everywhere we had x from before, we're substituting in x plus h. We now want to simplify this. We can distribute the 3 in. We get 3x plus 3h plus 7. There's no like term, so there's nothing more we can do here. That would be our simplified expression for f of x plus h. We now want to simplify the difference quotient, f of x plus h minus f of x divided by h. So let me start out by doing this. Whenever I do my difference quotients, I always like to kind of highlight the 3 key pieces. Remember, h will always go on the bottom. That's usually the easiest part. You can just put an h down there in the bottom. The first piece is f of x plus h. That's the answer to the last part we just did. We know that f of x plus h is 3x plus 3h plus 7. And now the thing we have to subtract from it is f of x. That's the original expression of the function. If you go back, the function was 3x plus 7, and so that's what's going to go here. I like to put these brackets every single time. First of all, visually, they kind of help us to go back and piece apart the difference quotient so we can see all 3 key pieces. This piece is the f of x plus h. You can see we're subtracting the f of x, and then you can see the h on the bottom. The other reason why it's important to put grouping symbols is that if we're subtracting f of x, and f of x has a lot of terms in it like we do here, we need to make sure that we're subtracting every single thing that belongs to f of x, and that will be seen in the next step. To simplify this, we can eliminate our grouping symbols by distributing. Let's distribute the negative 3x in, the negative sign in. That'll give us a negative 3x minus 7, all divided by h. In the numerator, not only do we have some common terms, but we have some like terms that'll cancel. Notice that we have a positive 3x and a negative 3x, so those cancel. We also have a positive 7 and a negative 7, and those also cancel. That now leaves us with 3h divided by h. Notice that our h's cancel, and for this one we have a final answer of 3. As a general guideline, whenever you're trying to simplify and set up a difference quotient, you know that you're heading in the right direction if near the very end of the process you should get the original h that was in the denominator to cancel out of your expression entirely to put it in simplest form. So here we get a final answer of 3. Let's do a couple more of these. In example 7, we're asked to find and simplify the difference quotient for the function f of x equals 2x squared minus x plus 3. So first things first, let me write out the difference quotient. Again, the formula is f of x plus h minus f of x, all divided by h. We have those 3 key pieces. We have h. We're going to have the f of x plus h. And then we also need to subtract f of x. The f of x part is easy. It's just whatever equation they give us. That's 2x squared minus x plus 3. The f of x plus h part itself will require a little bit of work. And oftentimes I like to do that off to the side, just so it doesn't kind of clutter up our main workflow of the problem. So over here off to the side, let's see if we can find f of x plus h. The statement form for our function is it looks like 2 times the input squared minus the input plus 3. Everywhere we see an x, we're going to replace it with an x plus h, like this. And now we need to simplify. Be very careful over here when we square this part. Remember, when you square something, especially a binomial, that means we have to multiply it by itself. So we're going to have to distribute this. For this term, we can just distribute the negative sign. Then we're going to get a negative x minus h. We still have that plus 3. Let's go ahead and distribute this out. X times x is x squared. X times h is xh. H times x is another xh term. And then h times h will give us h squared. We can simplify the two middle terms here. Xh plus another xh will give us 2xh. And then lastly, we can eliminate the parentheses by distributing this 2 in. There's no like terms, there's no parentheses, so this would be our simplified version of f of x plus h. And let's go ahead and plug it into our difference quotient. We have 2x squared plus 4xh plus 2h squared minus x minus h plus 3. We now want to simplify this thing. To begin, let's distribute, get rid of that grouping symbol up top. 2x squared plus 4xh plus 2h squared minus x minus h plus 3. When we distribute the negative sign in, we get a negative 2x squared plus x minus 3, all divided by h. And with that grouping symbol eliminated, now we can go ahead and combine like terms. We have a positive 2x squared, which will actually end up canceling with the negative 2x squared. We have a negative x, which will cancel with the positive x. We have a positive 3, which will cancel with the negative 3. And those are all of the like terms we can combine up top. If we rewrite this, what's left is we have a 4xh plus 2h squared minus h in the numerator, all divided by h. So we've done quite a bit. We certainly have simplified it. But remember that tip I just gave us a little bit ago. It'll be fully simplified if we can ultimately get that original h in the bottom to cancel. And we can do that because if you look at the numerator, there's a GCF. Every single term in the numerator has a common factor of h in it. So we can factor the h out of the numerator. That'll give us a 4x plus 2h minus 1, all divided by h. And now with that common factor, we can cancel the h. H in the numerator cancels with the common factor of h in the denominator, and we're left with 4x plus 2h minus 1. And that would be our simplified difference quotient for this one. Typically, it will be quite a bit of algebra to get to the end of one of these, but the key is to get into good habits nice and easy. Write down the formula for the difference quotient. Try to use grouping symbols to highlight the three key pieces, the f of x plus h, the f of x and then the h. Next, it's pretty easy to plug in these first these two pieces. H is always in the bottom. The functional equation they give you goes in the second part. And then, as a good suggestion, try to do the f of x plus h stuff off to the side. And then once you have that simplified, then you can plug it into your difference quotient and go from there. Let's take a look at one more example of a difference quotient. Let's find and simplify the difference quotient for f of x equals 1 over x. So first thing, we're going to start out by writing out the difference quotient like this. Here, there's not as much to do. F of x is just a single term, so you can omit the grouping symbols if you want on this one. This function, f of x, simply takes our input and divides it into 1. So everywhere we see an x, we're going to go ahead and replace it with an x plus h. So f of x plus h is simply going to be 1 over x plus h. So we've set up our difference quotient. We now want to go ahead and to simplify this thing. This isn't like a polynomial, so our function f of x this time is 1 over x, which we're going to call a rational function later in the class. But there's no like terms to kind of combine. So we could look at this and be like, well, what does it mean to simplify this kind of thing? Well, the answer is it has to be simplified because right now we have a complex fraction. This division bar was the main division symbol that was used in our definition of the difference quotient. And if we look in the main numerator of that fraction, it contains additional subfractions. So that makes this thing what's called a complex fraction. So we want to simplify this complex fraction. The way that I typically do this, is more than one way to do this. There's two different approaches. But if you look at all of your minor denominators or your subdenominators, let's identify their LCD. The LCD of the quantity x plus h and x is simply going to be the product x times x plus h. Once you recognize that LCD, what we can do is we can multiply every term in the numerator and denominator by that LCD to clear off the fractions. So this is a common technique. You can multiply top and bottom of a fraction by the same value. Let's multiply the top by x times x plus h, and also the bottom by x times x plus h. In the numerator, we're going to distribute it. We have 1 over x plus h times x plus h minus our 1 over x times x plus h, and in the denominator we have h times x plus h. If it helps, especially within the numerator, you could think of the x and x plus h over 1, because we're going to multiply it with a fraction. In the first expression, the x plus h's cancel, because you have a common factor on top and bottom. And that's going to leave us with a 1 times x over 1, which is just x, minus, in the second term, notice that the x's are going to cancel, and we are simply left with 1 times x plus h, which is x plus h. In the denominator, we have this product. I'm just going to leave it there. H times x plus h. To simplify from here, leave the denominator factored, but distribute the numerator out. We have x. This will now become a negative x minus h, all divided by h times x plus h. In the numerator, the x and negative x cancel, so we have negative h divided by h times x plus h. And now we know we're at the end because we're able to get the common factor of h in both top and bottom to cancel. So we have a factor of h in the numerator, a factor of h in the denominator, Those cancel, and we're left with our final answer of -1 divided by x times x plus h. And that's what the simplified difference quotient would look like for this example. In example 7, one of the things that we oftentimes want to know is when a function value would give an output of 0. Those kinds of numbers will have very important consequences and meanings later. For example, these are going to correspond to x-intercepts. They're also called zeros or roots of the function. But here, it's just simply a matter of taking the functional equation, setting it equal to 0, and then solving for x. With this one, this would mean solving x squared minus 5x plus 6 equals to 0. This gives us a quadratic equation. We have many different ways to work with these. Luckily, this one factors, and it's going to factor as x minus 2 times x minus 3 equals to 0. We can set each factor equal to 0 from the zero product property of the real numbers. Add 2 to both sides for the first one. Add 3 to both sides for the second one. And we get two solutions. X equals to 2 and x equals to 3. Those are values in the sets are special, and that those are the two values of x that you can plug in for this function to get a 0 output. Okay. You don't have to check them. I just to show you. Let me plug 2 in. According to what we've just solved, if I plug 2 into this function, this should yield or produce an output of 0. Everywhere we see an x, we put a 2. 2 squared is 4. -5 times 2 is -10 plus 6. And sure enough, 4 minus 10 is -6. -6 plus 6 does give us 0. So there'll be many different instances where we want to solve for the zeros of a function. That simply means setting its equation equal to 0 and then solving the resulting algebraic equation. We also might want to know where two functions have equal outputs. In other words, for what values of x can we plug them into the function f and into the function g and get exactly the same output, meaning when is f of x equal to g of x. To solve that, we're going to take the two equations, take the equation for f, which is x squared minus 1. We're going to set it equal to g of x, which is -x squared plus x plus 2. And now we're going to solve this equation. It's going to be a quadratic. Easiest way to do this is we want to get one side to be 0. So I'm going to clear off the right-hand side. I'm going to add x squared to both sides. I'm going to subtract x, and I'm going to subtract 2. Everything on the right-hand side cancels and gives us 0. X squared plus another x squared will be a 2x squared. We have a -x, and then a -2 and a -1 will make -3. Another quadratic equation. This one luckily will factor again. We have 2x and x. We're going to have a 3 and a 1. There should be a negative and a positive. Once it's factored, we set each factor equal to 0. For the first equation, we would add 3 to both sides. And then the next step would be to divide both sides by 2. So we get one value is x equals to 3/2. For this one here, we would simply subtract 1 from both sides, and we get x equals to -1. Again, going back and thinking about what does this mean, if we were to plug either -1 or 3/2 in for x, the functions f and g would produce equal outputs. And we don't have to, but I'll just go ahead and check this. And I'll just use, let's say, -1. If I plug -1 in for f, negative squared minus 1 is 1 minus 1, which is 0. So plugging -1 in for f gives us an output of 0. And if we plug -1 in for g, this is the opposite of -1 squared, plus -1 plus 2. That's going to be a positive 1, which changes to a negative, another minus 1, and then a plus 2. And sure enough, that also produces the same output, which in this case just happens to be the value 0. The next topic we're going to talk about more in depth is the domain of a function. The domain of a function can be described explicitly, or it can be implied by the expression used to define the function. The implied domain is the set of all real numbers for which the expression is defined. So unless the restrictions are explicitly stated, the domain as it's understood for a function is the collection of all values x in the domain that we can actually get a output for the function. If a function does not model data or variable conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. So again, for the domain, it's the values we can plug in so that we're able to get an output f of x. In order to find the domain, we oftentimes will kind of ask the opposite question. In other words, what things can't we plug in, or what kind of values cannot compute? And for right now, the two restrictions we're going to have is if we plug in a value that results in a division by 0, that will not produce a real number. Division by 0 is undefined. So we need to make sure that if we have any fractions or any situations that result in division by 0, those values of x will not be included in the domain. The other thing that we will be looking at right now is if we have any square roots or even roots, so square roots, fourth roots, sixth roots, etc., we can only take an even root of a non-zero number if n is even. Okay. So if you have a square root, fourth root, etc., we need to make sure that the quantity under that radical is greater than or equal to 0 in order to evaluate it as a real number. In example 9, part A, we're asked to find the domain of g of x equals 1 divided by x plus 5. Here, we do have a denominator. To find the domain, let's set the denominator equal to 0 to see what values of x would give us division by 0. We can subtract 5 from both sides, and we get x equals -5. That one value, x equals to -5, when we plug it in, we see it gives us division by 0. So x cannot be equal to -5. Any other value of x on the real number line is okay, with the exception of -5. What that would look like is we'd have the entire real number line, but we'd have a hole where -5 is being excluded. Typically, whenever we write the domain of a function, properly speaking, we want to write it in interval notation. This would be the set from -infinity to -5 not included, so it gets a parenthesis, union 5, -5 to positive infinity. As long as x is in this set, then we are able to plug it in and we will get an output for the function g of x. So that is the domain of g. Sometimes you'll just see me write d equals. If we have more than one function, sometimes you'll see me put the function name as a subscript. So if you see me write d sub g, that just simply means the domain of the function g. Let's take a look at part B. We want to find the domain of h of x. Here, h of x does have an even root. It's a square root. So we need to make sure that the quantity on the inside of that root, the 4 minus 3x, has to be greater than or equal to 0 for us to evaluate it as a real number. We're going to solve this inequality. We begin by subtracting 4 from both sides. We get negative 3x is greater than or equal to negative 4. And then the next step to get the x by itself, we have to divide both sides of that inequality by negative 3. Keeping in mind, whenever you do that, dividing or multiplying an inequality by a negative number is going to change the direction of the inequality. So this will now become x is less than or equal to positive 4/3. On the number line, somewhere we would have the value 4/3. Less than, we know, means go to the left, like this. And the 4/3 would be included. So you can either do a bracket or a filled in parenthesis because of the less than or equal to part. And so the domain for this function, we would write domain of h. It's the set from negative infinity up to and including 4/3. Any value in the set, we're allowed to plug into h of x, and we will get a real value output from it. The next example we have is the function v of r equals 4/3 pi r cubed. Here we don't have any divisions by variables. We don't have any roots. So the domain of this function is going to be all real numbers. You can write all reals, you can put all real numbers, the stylized r sign, or another way to write it would be the set, the domain of v would be the values from r from negative infinity to positive infinity. Or you can put all reals.